Astronomers have managed to discover a nanoflare on the Sun. The prediction of this discovery was done approximately 5 decades ago, and astronomers believe that this will solve a major mystery. Astronomers have found the long-sought-after nanoflares, which they believe heat the solar corona to its incredible temperatures. According to astronomers, this is the first time that they have captured the full life cycle of a putative nanoflare. They managed to watch it from its bright origins to its blistering demise. Nanoflares are tiny eruptions on the Sun, and they are considered to be a major puzzle. Whilst they are minor or mini flares, they will solve the coronal heating problem for astronomers and researchers alike. Nanoflares are 1/1000th the size of normal solar flares. They were first predicted in 1972, and they will solve a major puzzle, the coronal heating problem. The coronal heating problem is the mystery about how the Sun's outer atmosphere, or its corona, gets so incredibly hot. Despite being much farther away from the solar core, it's millions of degrees hotter than the layers beneath it. Nearly 5 decades later, the coronal heating problem still has not been resolved. It has been hard to confirm any of a handful of different theories, in part because no one has ever actually seen a nanoflare. Nanoflare is just one of several mind-boggling facts about the Sun. These problems or facts about the Sun are extremely hard to solve, and sometimes when researchers and astronomers are trying to observe the various areas or specific atmospheric items on the Sun, it is very difficult to observe. Nanoflares are tiny and short-lived, and even our best telescopes on Earth have only recently become powerful enough to resolve these problems. Therefore, seeing a tiny flash isn't enough. It takes a lot to be considered a true nanoflare sighting or observation. As researchers, we know from theory that we should look for what fingerprint a nanoflare would leave. A nanoflare by any other name cannot be considered the same. To say that you have observed a corona heating nanoflare, you have to check at least 2 major boxes. First, like regular flares, a nanoflare is set alight by magnetic reconnection. If the eruption you're seeing is heated by some other process, it is not a nanoflare. Magnetic reconnection is triggered when magnetic field lines explosively realign. Unlike other mechanisms that heat things up gradually, it can take relatively cool plasma and make it super hot in an instant. Nanoflares are like putting 2 ice cubes together, and suddenly the temperature rises to 1000 degrees Fahrenheit. One way to observe heating via magnetic reconnection is to observe intense heat amidst far cooler surroundings. Second of all, the nanoflare has to heat the corona, which might lie thousands of miles above where they erupt. That's not a minor issue. Many other solar eruptions only heat their immediate surroundings. Therefore, as an astronomer and a researcher looking at a nanoflare, you have to examine if the energy from a nanoflare can be dissipated in the corona. If the energy goes somewhere else, that does not solve the coronal heating problem. At the beginning of this project, the team would have decided to investigate some tiny bright loops at about 60 miles across. They are tiny on the sun scales, But of course, the team would have noticed flickering in the layer just below the superhot corona. They thought that maybe the loops made the surrounding atmosphere hotter. They never thought, however, that it would make so much energy that it might actually propel hot plasma to the corona and heat it up. As they continued to look more deeply into the images that were taken by NASA's Interface Region Imaging Spectrograph, or the IRIS satellite, they realized two massive findings. First, they discovered that these loops were incredibly hot, millions of degrees hotter than their surroundings. But even stranger to these researchers was that the heat was distributed in an unusual way. It was different from that in most other physical systems. While the sun is made mostly of hydrogen and helium, it also contains smaller amounts of every other element. In these loops which are observed, the heavier elements such as silicon, which has 14 protons in its nucleus, were much hotter and more energetic than lighter elements such as oxygen, which has only 8. Of course, according to the research team, if you were to push a ball that is very light across the floor, it would roll farther than a heavy ball. Yet, in this case, the heavier elements were shooting out at about 60 miles per second, while the lighter ones were almost at 0. And according to the research team, this is utterly counterintuitive. This strange observation told them that something very specific must be happening in the bright loops, and that was their massive clue. They managed to realize that at the start, they're thinking about what kind of heating could impact the oxygen atom differently than the silicon atom. They spent many years running computer simulations and models, testing out different heating mechanisms, and they finally found one that could match their observations, which included the heating of the heavier elements more than the lighter ones. In the end, however, only one heating mechanism could produce the effect. The heat had to come from a magnetic reconnection event, the same driving force behind solar flares. The key was in the aftermath. As magnetic field lines twist and realign, they create a brief electric current that accelerates the newly freed ions. It's like everyone in a room is trying to run at the same time. They start to collide with each other, and there's a huge mess. Critically, the larger or the longer an ion can keep moving in an electric field, the more energy it gains. This is where heavy ions like silicon have an advantage over those that are lighter. Since they have more momentum, they can plow through the crowd and steal all the available energy. Therefore, the more massive silicon ions pushed their way through the chaos, soaking up the energy from the electric field. The lighter oxygen ions couldn't do that, however. They were stopped, and they had to gradually slow down after each collision. This mechanism would further go on to explain the results by the researchers. The simulations indicated that this process only happened under quite specific conditions. To make this happen, they needed a specific temperature, and they needed the right proportion of silicon to oxygen. So they looked back at the experiment and checked the measurements and saw that the numbers exactly matched. Remarkably, the conditions on the sun mirrored the simulations by the research team. The bright loops appeared to be tiny flares, but did their heat actually reach the corona? The team looked at NASA's Solar Dynamics Observatory, which carries telescopes tuned to see the extremely hot plasma only found in the corona of the sun. They managed to locate the regions right above the brightening shortly after they appeared. And after a 20-second delay, they saw the brightening, and then they suddenly saw the corona got superheated to multi-million degree temperatures. That gave them the important information that they needed. Yes, indeed, increasing the temperature transferring energy to the corona. They have managed to document 10 instances of bright loops with similar effects on the corona. Still, of course, they are hesitating to call them nanoflares. No one actually knows because nobody has ever seen it before. They call it an educated guess. It is very cool that they have discovered this hot and amazing discovery of nanoflares heating the corona of the sun. Like, comment, share, and subscribe. Let me know what you think about this discovery of nanoflares that will lead to the solution for the coronal heating problem. Thanks for watching. Goodbye.